Hello, everyone. My name is Ulf Stein from the Ecologic Institute, and it's a pleasure that we meet here today for the Future of Water Reuse session. And I have the pleasure to have two excellent speakers here today. The first one is Professor Bayenbuch, and the second one is Dr. Marcel Schneider, and we will dive into the topic and try to cover it from different perspectives and angles. And we start with a presentation from Matthias Bayenbuch. And you probably know him. He's a professor, head of department for urban water management at the Technical University here in Berlin. And his main research topics are wastewater, sludge management, and water reuse. Yeah, and he's also vice president of the German Association for Water Management, Wastewater and Waste, DWA. Yeah, and he's also known author of several publications and also head of different working groups. And without further ado, I will try to get him in today. We had some technical issues. I hope it works now. So, Mr. Bayenbuch, it's your go.
So, hello. After some technical problems, can you hear me now? Please give a short information in the chat. Okay, it seems so that you can hear me. Then we can start about the real topic, water reuse in urban areas. Some experience from our project, which we had together also with Mr. Stein from Ecologic Impact on Climate Change on Water Availability in Germany. So we did it for the environmental office agency in Germany together with Research Center Jülich and the Ruhr University. So maybe we can go to the next slide. So some motivation. Actually, we have the pressure of the climate change, and especially in Germany, we have huge problems. You can see in the last years, the temperature was rising, and this is also causing a water shortage that we have to face. And if you have a look on the world, there we have 1 degree increase, and in Germany, we have already 1.6 degree increase of the temperature. So that's why we think about water reuse, not only in Germany, worldwide, it's already applied. And especially also in Europe, we have some regulations for water reuse in agriculture. So water reuse is obtained water from treated wastewater, which is specially treated after the regular treatment. And then we can apply it maybe in agriculture. And I will focus on urban reuse. Already in industrial reuse, there's a huge recycling of water, and some countries also use it for drinking water. So we have to take into account, of course, health, environmental risks, and also local legislations or regional legislations. I have here an overview of some regulations given here in Europe and also in Northern America. We have here the biological parameters, the standard parameter, the indicator parameter is the E. coli, and you can see the E. coli is limited nearly in each regulation all over the world. By the way, we see here 10 in Italy is very ambitious. So if we look at bathing water, we have 500, and also we have a standard in Germany about that. Also, other biological parameters are regulated in some countries. Specifically, I want to focus on the helmet X. Helmet X mainly appear in the southern part of our global world, and so they can easily be removed by sieving. So also the chemical parameters I want to mention, maybe have a short look in the second line, COD. COD is also limited in several regulations all over Europe and in the world. Just by the way, you see here 70 up to 120 milligram per liter. Then you can use it for reuse this water, the German effluent value, the average German effluent value of all wastewater treatment plants is 26, just without any additional treatment. So we can go ahead. The spoken word is valid. That's for true. So it doesn't matter what is written on the slides. So now you can see my slide. There's a selection of systems for urban irrigation, and you can see nearly, not nearly all apply a sand filtration with a disinfection. And we have a long time of experience in that. And also here you can see the COD again, 22 to 80 is the average value. And you can see also the maybe no chance. You can also see the nitrogen, which can also be used as a fertilizer for agricultural land, but also for urban land. So I have taken here some examples which I had several years ago when I visited Australia. You can see here the flower, which are irrigated with wastewater. Also tomatoes, no problems, can grow, and also Christmas trees, of course, will grow. And golf places, unfortunately, I haven't catched the kangaroos, which also like this water and this green on the golf places. So maybe the best practice results show up. Urban water has been a stable and successful application for several decades already. Always 3-stage treatment in the wastewater, subsequent or a sand filtration and the disinfection is applied. We have also looked for the prices. So the price of the treated water is maybe 60% of drinking water price. So we have also savings if we apply treated water. And we have also a synergy when we need advanced wastewater treatment. So for Germany, we looked, as I mentioned, the threat on the temperature and the threat on the water availability. We looked what is possible, what is needed for the water demand for the urban green. So the needed amount of irrigation water for the urban green. And there we looked at the urban areas. So unfortunately, there is no real statistic about that. So we calculated 5 different approaches. Also, we don't know what kind of green grows on this urban area. So we took grassland and we calculated the climatic water balance. And you can see here, normal years, we calculated from 1916 and up to 2020, and dry years, these are the 12 driest years in this period, and the very dry years is 2018. 2018 is the driest year we had in this period. And then we differentiated between large cities, so maybe larger than 100,000, middle cities and small cities. And you can see here, this is the amount of water which is maximum needed for irrigation if we have all the green areas in the cities. And also we calculated the availability of wastewater. So there we need 15% of the wastewater. So we have 9 billion cubic meter per year. So 15% of that should be needed when we have an irrigation of all the city greens. So otherwise we have to consider risk management. So there is the European regulation for agricultural reuse, and reclaimed water has to be managed safely and does not pose any risk for the environment, for the human, and also for the animals. we build it up, this risk management, also according to the EU regulations, specifically related to urban greens. And we made a 4-step approach, entire water reuse system, describe the entire water reuse system from the discharge point, so the wastewater treatment, also the industry which is connected to the wastewater treatment plant, and up to the point of use. Then we have to consider all parties which are involved, the treatment plant, of course, the distribution company maybe, and also the green savers. And we have to describe the roles and responsibilities. We have to consider and identify the hazards of pollutants and pathogens. And in the end, we have to consider about the environmental risk, and also, of course, of the risk of the people who will use the urban greens. And then we set up the boundary areas. You can see here, this is the wastewater from the household, from the industries. We have to look at the composition of the wastewater. We have to consider the advanced treatment, disinfection, sand filter always is recommended. And then also who will use the urban green, maybe only people from the green authority, also public, and maybe also only sportsmen. And also we have to consider when and how is the use, yeah. And then we have this, yeah, to distinguish between different greens. We have to also to look at what happens when we irrigate too much, yeah, so that infiltrates into the groundwater. We have to consider the quality of the groundwater, specifically also with the micropollutants and so on. And in the end, we can set up possible measures for the precaution. Yeah. Access controls, for example, additional disinfection directly while the irrigation, also specific irrigation technologies, drop irrigation, drip irrigation, and so on. Also, maybe opening times, adjusting the opening times. So just after after irrigation that it's forbidden, maybe waiting for several hours. The requirements for the urban green have to be considered. The slope, also maybe safety distances between neighbors. And in the end, we have to also set signs. Yeah, maybe here I have an example at a golf club. So this is not potable water, and you have to wonder when you make a jog or run there. Also, you have to be careful. So we, in the end, we made an example. What do we have to consider if we will build up an urban irrigation system? So we have on the left-hand side a pipe system. So this is a wastewater treatment plant. There's enough water available. And then we have a pipe system here. We consider and made a rough planning of a pipe system, also a storage tank. And on the right-hand side, we have the road tree irrigation, which we suggested to do this by trucks, yeah, so for the road trees. And this, in the end, of course, this might be more expensive than drinking water, but we have a recycling of the water and we can improve this. And in the end, we have to think about whether we really want to supply water to all the urban greens. Finally, we made a stakeholder survey, and I just took the graph of acceptance, the results of the acceptance, and we asked about the attitude. Could you imagine whether you use recycled water for urban purposes, and maybe look of course, hygienic and health regulations will be regarded. So, and you can see here, 85% agreed with this. 85% would use recycled water. Of course, they need a certain threat. Yeah, a lack of water, then they would use it. We can see here, of course, we can see the science has no regrets, but other, maybe the firefighters, they have some remarks on that, and they have to be adjusted. So I just want to thank you for the attention, and please find partners who treat wastewater and who need to use it, and then we have to set up the rules in between this and make good content. Thank you very much for the attention.
Yeah, thank you, Matthias Beinbuch. It was a very interesting talk. You see people applauding. I know that our audio connection isn't that good, so I probably will not ask any question as Mr. Beinbuch is already leaving the room. Maybe we come back to this later, because I have some question actually for both speakers. So then I now will take the opportunity to move on to our second speaker, which is Marcel Schneider. He is working for the Leibniz Institute for Plasma Science and Technology in Greifswald, and where he's responsible for the topic of clean water, focusing on the application of plasma methods for the removal of pollutants. And so I already see the presentation. So Mr. Schneider, please start the presentation. Thank you.
All right, thank you very much for the introduction. And yeah, good afternoon to the audience. So as Mr. Stein just mentioned, my name is Marcel Schneider. I'm from the Leibniz Institute for Plasma Science and Technology in Greifswald in Germany. And in my presentation today, I want to share some of the highlights of our work and provide some insights into how plasma technologies can be applied for water treatment and reuse. So first things first, plasma is often considered or often described as the fourth state of matter. So if we start on the left-hand side with a solid, we supply energy, it turns into a liquid. If we supply more energy, it turns into a gas. And now if we supply even more energy, in this case, we usually use electric energy, the gas will be ionized. And that's exactly what a plasma is, a reactive ionized gas. Most people are not really aware, but plasma technologies are already widely used in different applications and industries. It's just that it's usually hidden in the final product. So one example I want to mention here, because it's relevant to today's topic, is the generation of ozone. Like at industry scale, ozone generators usually are based on plasma. Now, if we want to produce a plasma, we basically need a setup with two electrodes, these gray bars in this picture here. And now if we supply a high voltage, an electric discharge will be propagating in between these two electrodes, and that will produce the plasma and also induce various physical and chemical processes. These processes include, for example, the emission of light in the ultraviolet and visible spectrum, and it will also produce various different reactive chemical species. And these processes can now be exploited for water treatment to inactivate microorganisms and degrade organic compounds. In context of water treatment, the plasma technology comes with a set of unique advantages. So in order to produce the plasma, basically all you need is a plasma reactor, electricity, and in some cases, a gas, which usually is air. But other than that, you don't need any other chemicals, catalysts, or other additives. And the plasma can inactivate microorganisms, including multi-resistant bacteria. And so far, there is no evidence pointing towards the development of microbial resistances against plasma treatment. The plasma can also degrade organic compounds, and even those that are not properly addressed or are not susceptible to other advanced treatments. Another huge advantage is that the plasma system can be adapted to specific situations and requirements. So depending on the discharge configuration and the operating medium, these physical and chemical processes I mentioned before can be controlled to some extent. And that makes the plasma technology quite versatile. And yeah, last but not least, plasma systems are usually quite easy to handle, and they allow for an on-demand operation. So you can easily turn the plasma system on and off as needed. Now, if we want to treat water with the plasma, we need to make sure, or we need to bring plasma and water into contact and make sure that they can interact with each other. To achieve this interaction, or to realize this interaction, we basically have three different principles. The first one is shown here in these two examples on the left-hand side, and that's discharges in gas. And then the gas, or the plasma treated gas, or the plasma effluent is brought into contact with water. The most prominent example is shown up here, and that's basically how ozonation of water works. The second principle, that's the four drawings in the center, that's discharges in contact with water. And here we have different setups that can be used. So we can either direct the discharge towards the water surface, or the discharges can spread along the water surface. And another example shown in these two drawings is a water spray through an electric discharge. And the third principle is then shown here on the right-hand side, the two examples. These are discharges submerged in water. And here we have, so to speak, the most immediate interaction of the plasma with the water and the contaminants in the water. This topic of water treatment has been established about 10 to 12 years ago at the IMP. And since then, we had a lot of different studies, a lot of different projects where we developed different plasma systems and used them for different applications. So on the next two slides, I'm going to just show a few highlights. And the first example is the degradation of pharmaceutical residues. And here we use the discharge submerged in water. A picture of how it actually looks like is shown down here. As you can see in the plot, we could quite effectively degrade even persistent and recalcitrant compounds like this contrast agent. And in particular, diclofenac and ethinyl estradiol were quite effectively degraded by more than 99 and 95%. Then moving on to the next example on the right-hand side, here we use the water spray through a discharge. Again, here's a picture of how it actually looks like. And one of the examples where we use this setup is the treatment of hospital wastewater with a goal to reduce or to inactivate antibiotic-resistant bacteria. As you can see here in the plot, we were quite effective, so we could, in different water matrices, achieve a reduction of more than 2 log steps and even up to 99.96%. Another set of compounds that we are also looking at are pesticides, and here on the left-hand side is an example where we use the discharge that spreads along the water surface. And here we could degrade glyphosate by more than 90% in just 30 minutes of treatment. And then again, another example on the right-hand side, that's again a water spray through the discharge. It's similar or a similar principle to the example I showed on the previous slide. It's just a different geometry of the setup. And with this system, we treated PFAS, or also known as forever chemicals. And now if we take a look at plot on the top, we can see that we could degrade a compound, PFOA, so probably one of the most commonly known PFAS compounds, and we could degrade it by more than 16%. Now, 16% doesn't seem to be much, but considering how stable and persistent these PFAS compounds is, more than 16% degradation is quite a good, quite good result, especially considering that the sample was treated once, so it just passed through the system once. Now, in the next set of experiments, we then obtained the wastewater effluent from a nearby wastewater treatment facility. We added PFOA and then treated again with the same system. The data is shown in orange, and we have 5 data points, which basically means the sample was treated 5 times. And that corresponds to roughly 12 to 13 minutes of treatment. And here we could achieve close to 70% degradation of PFOA, which again, quite good results for this very sturdy and recalcitrant compound. So now these 4 examples, they are all examples from laboratory scale experiments. Although we used real water matrices in some of these studies, they were still conducted under rather controlled environments and controlled conditions. So in a current project, which is called Physics for Environment, we then wanted to go one step further. So out from the laboratory and into the field and test the system under real life conditions. So together with partners from the industry, we built a demonstration unit, which is shown here in the middle. And in this system, we combined plasma with several established technologies like ozonation and activated carbon filtration. The system is currently in use, or is currently used to treat the processed water of a sugar beet factory. And once we're done once we have enough data, we will move on to a brewery and validate the results. The system is set up right now to treat up to 2 cubic meters of water per hour. And it's a modular setup, which basically allows us to adjust and change the order of the different treatment methods that are installed in the system. And with that, we can basically, for each application, for each water matrix, we can, well, find the best treatment option or the best order of treatments. For the Physics for Environment project, the focus was mainly on, or is mainly on treating water from agriculture and food industry. And the goal is to eliminate bacteria and chemical pollution, in particular pesticides. And basically, we want to treat the water and purify the water to an extent that it can actually be reused in the food industry. The results we've obtained so far indicate that plasma is competitive compared to, for example, ozonation. And the next steps are now, well, basically further upscaling of the plasma systems. And yeah, the examples I just showed are, of course, only like the highlights of our work. We have many more different applications where we develop systems, plasma systems, and treat the water. And here just a few more examples where for possible applications. So one of our main goals, or one step we try to achieve, is to establish plasma treatment for decentralized treatment at the hotspots. So basically at the place where the pollutant load in the water is the highest. For example, wastewater from hospitals and chemical and pharmaceutical industries, or the leachate from landfills. And of course, water treatment in general is not our only goal. We're also looking into possible applications where the water is actually reused. We have currently a few projects where we look into that. One of the projects is the Physics for Environment project that focuses on the food industry. And we also have several projects that work on aquacultures, hydroponics, and vertical farming. And we also are about to initiate a project that focuses on the water reuse from laundries. So basically, the idea is to treat the water and then reuse it while it's still warm instead of using or heating up again cold water. And besides reusing process and then wastewater, of course, we're also looking into using rainwater, for example, as an alternative resource or alternative source, in particular for irrigation in the agriculture. So as a take-home message, I'd like to summarize that plasma is a promising technology that can help us in achieving sustainability in the water sector, in particular with regard to water treatment and reuse. Yeah, thank you very much for your attention, and I'm looking forward to your questions and an interesting discussion. Thank you. I think it's still muted, Mr. Stein.
Thank you very much. Yeah, so thank you very much for this really great talk. And it was very inspiring. And we can already dive into a couple of questions that I've noted down. Maybe there are also some questions from the audience. But let me first start with the question, where do you see, I mean, you explained very well how plasma technology works, and maybe also how it differs from traditional water treatment, but where do you see the main pros and cons of the technology compared to our conventional treatment methods?
I will start with the negative side, so with the cons. I think that the main issue we have right now is the upscaling. We know from ozonation that upscaling is definitely possible, but with the example ozonation, I think that took decades to bring it actually to a level where it can be applied for like cubic meters per hour. So that's one of the main issues we're facing right now. So we try to, in projects and together with industry, to find solutions for that. And with the upscaling, so it's not only referring to treating higher quantities of water, but also in particular optimization in terms of electric efficiency. So I think that's one of the points, the efficiency. It is probably more expensive right now as established methods, at least to some extent. But on the other hand, like the pros, we have shown that we can degrade even persistent compounds that are not susceptible to, for example, ozonation or even other advanced oxidation processes. So I think that's the biggest pro. And of course, the on-demand treatment. So the versatility of the plasma system can be rather small for like private households, can also hopefully be upscaled to larger quantities.
Mm-hmm. Maybe you can give us an indication. I mean, how would you see the technical readiness level of this technology?
I would say, so we have several different systems up and running, and I would say for like 2 of the systems we're currently focusing on, they have a TRL of about 5 to 6.
Okay.
So that's in particular the one system, that's the water spray through through the discharge that we already that we also used in this demonstration unit in the Physics for Environment project.
Mm-hmm.
So with this system, so with this system we can already treat like a couple of 100 liters per hour, which is still a long way to go, of course, but we're on track.
Okay. I also learned, and I found it very interesting, that the technology is also good for decentralized application and on-demand application. So this actually sounds for me as a perfect fit for water reuse purposes, especially in urban areas. So if you think about breweries, you mentioned the examples, and you maybe have a nearby green area that you want to irrigate, then I mean, it would give the advantage that you don't have to build a lot of pipes, right? So is that something you're looking into?
Yeah, and indeed we do. So also within this Physics for Environment project, so we now have this demonstration unit, which is like a 20 feet shipping container, which is already kind of mobile. And we also plan to design and build smaller units, which can actually then, for example, for the agriculture, be used on the field. So mobility is a strong pro for the plasma technology, and in particular because we only basically need electricity and the setup itself. And also with the advances in like solar power and wind power, I think that's a good thing for the future, also for decentralized treatment.
Okay, very interesting. I would like to move on to the next topic, and I also want to take up some of the questions that are coming here from the chat. So let me move to the whole topic of health and safety. Maybe some of these questions you hear a lot. So there was one question: how do you control potential dangerous metabolites, for instance, during treatment of water with organic compounds?
Yeah, so basically, plasma is one of the technologies that can be used within a multi-barrier treatment chain. So similar to other oxidation processes like ozonation, there probably needs to be another step following up the plasma treatment. For example, activated carbon filtration. So yeah, the longer we treat, the more we can actually degrade the compounds, but that's always a question of what's the goal or what are the requirements and how expensive and time consuming can the treatment be. So with enough time and energy, we can probably close to mineralize these compounds. But if we're limited on that hand, we probably need to, similar to other systems, have like a filtration step or another treatment step after the plasma.
Mm-hmm. And maybe also another question that came up here is related to the removal of micro nanoplastics. Is that also a field where you're working on? I mean, we've seen PFAS, but maybe there's also this topic that you have on your agenda.
We have indeed talked about microplastics in our group meetings, but we have no experience yet. We know from colleagues from the plasma community that plasma treatment can, well, at least modify the surface of the nano or the microplastics to an extent where sometimes they can actually be disrupted. But I think the biggest issue then would be, I mean, microplastics can still be filtered out of the water, whereas nanoplastics, that's a different topic. So even though I really like plasma, I think for microplastics, the best solution is probably filtration.
Okay. Yeah, that will be interesting for many of those who are working on this topic. I move on with some of the questions, and we have really some really nice questions here from the audience. So there is a question: what are the biggest challenges in operating and maintaining the system? we already heard about energy consumption, but maybe you can, elaborate a bit on this.
Well, I think that's similar to other setups as well, or to other technologies. So there probably needs to be regular maintenance on the reactor or the system. So we use metal electrodes usually. Depending on the discharge, there can be some erosion of the electrodes. So we need to, or we may need to exchange these electrodes. But other than that, I think, like I said, they're usually they're easy to handle, and the systems are usually quite stable. So there might need to be some maintenance every once in a while. And of course, you need to make sure that the system runs properly. So you need to have like automation and possibly some kind of remote control to basically watch over the system. But I think these are really the biggest challenges. So it's rather small.
Yeah, okay. And maybe one last question while we slowly coming to the end of the session. I mean, there was also a question about are these treatment reactors still prototypes or industrialized models?
So the systems we work, they're all basically DIY systems. So we build them in-house, and I think there are a few companies that actually produce larger systems and at an industrial scale. But yeah, as I mentioned, in our systems are all still prototypes. And of course, we're looking into like upscaling and developing, and also together with industry partners, we want to move further and then bring the plasma systems into like real life applications and to a market ready product.
Okay. And maybe like, I mean, you're really an expert in plasma technology, and I would be interested if you look into the future. I mean, can you give us a vision where we stand in 5 years from now?
Good question. Hopefully we will have systems for variety of like quantities to treat, so from small scale to large scale. And we're always working hard on like finding new projects and new partners to further develop the systems, and also to show that plasma can be used in all kinds of different applications. So as I mentioned, I only showed a few highlights, but of course basically all kinds of applications we can think of. So yeah, hopefully we will have systems that can actually be sold through the industry.
Yeah. Okay. I mean, we have still 3 minutes, and I couldn't use this for more questions. I think it was very interesting, not only for me, but also for the audience. There are a lot of questions, and I think probably a lot from different angles. There are options to team up with you also in the future. There are a lot of researchers here. Maybe one last question, because we have the time. How is plasma technology different from electrochemical treatment? Or is it just can be considered as a kind of electrochemical treatment?
I must admit I'm not an expert on electrochemical oxidation or electrochemical treatment, but from my understanding, yes, there is a difference. The entire systems look different or are different. We have different electrodes, and we also use different power supplies and then different voltages and currents. And electrochemical oxidation, you have reactions at the electrodes or at the surface of the electrodes, and then you produce also reactive species. And the difference here is with the plasma, we produce reactive species in a different way. So I think that's the main difference.
Okay, now I also have a question for Mr. Beinbuch, who just told me that he's now ready to answer questions. I have a question for him. Maybe he can read it. I mean, it's like, how do you envision the future of water reuse in Germany, and where will we be standing in 5 years from now? So, Mr. Beinbuch, if you want, you can end up the session with a statement from your side.
Yeah, okay. I think it depends on the availability of water, if it's running drier and drier. So we have to change the system. We have to think about the reuse of treated wastewater. And as I mentioned in the end of my talk, we always need partners, someone who needs the water and someone who can provide the water. And that would be yeah, the challenge, I would say, not the problem, the challenge. And I guess we will have several further applications in the future, also in the near future, as when we say 5 years is the near future.
Okay, thank you very much. Thank you very much from all. Sorry, who's speaking? So I think we have to stop the session now. My alarm clock is ringing. Thank you very much. Thank you to the speakers, to the audience for the lot of questions that we had. And see you back in the big plenary. Goodbye. Ciao.